Alright, a warm hello to everyone who's watching. I'm delighted to finally present our work, Spying with Your Robot Vacuum Cleaner, Eavesdropping via Lidar Sensors, which is a collaboration between the National University of Singapore and the University of Maryland. I'm Sriram, and I'm presenting this work on behalf of my co-authors, Yimin Dai, Sean Tan, Nirupam Roy, and Junhan. I'd like to start with the fact that autonomous systems are continuing to become pervasive today. Self-driving cars are perhaps the most well-known, but industrial robots, delivery robots, and even in today's case, robot vacuum cleaners are gaining popularity. One of the most critical tasks for autonomous systems is navigation and mapping, since they need to find their own way through any given environment. So if we look closer at these systems, they have one thing in common: a LiDAR sensor for navigation, which is a laser-based distance sensor. They're even in smart devices at home, like this robot vacuum cleaner. And speaking of smart devices, there are good reasons to be afraid of smart devices in general. There is just constant news that another smart device has been compromised with pretty scary implications. And we have bad news. Turns out we found yet another attack on smart devices. In the rest of this talk, we will show that robot vacuum cleaners with LiDArs are a threat to your privacy. We convert the LiDArs on robot vacuum cleaners, supposedly used for navigation, into a stealthy microphone to spy on you at home. Our work is inspired by the idea of laser microphones, a spy eavesdropping device used since the Cold War. An attacker fires a laser at a window. Assume there is a private meeting happening behind the window, let's say in a meeting room. Speech inside the room vibrates the windows of the room. The attacker measures some properties of the return laser to recover the audio happening inside the room, and this is the fundamental principle of a laser microphone. So let's look at how these laser microphones work at a micro scale. Here, we have a laser microphone targeting a reflective surface like a window. If there is no sound, the laser microphone receives a constant amount of light back to its receiving sensor. If there is sound, the window flexes and vibrates, here an exaggerated illustration, and the amount of light received changes over time. This changing light intensity signal is almost exactly the same as the source audio itself. So we take this high-level idea of laser microphones as an inspiration to present our work, LidarPhone, which is a remote, stealthy, and scalable acoustic eavesdropping attack. Here we present an exemplary scenario. A potential victim attends an online Zoom meeting where sensitive information is being discussed. For example, social security numbers or passcodes. The speech from the meeting vibrates nearby objects like trash cans. LidarPhone compromises the victim's robot vacuum cleaner and targets the trash can to record its vibrations. We transmit a raw laser intensity stream from the robot vacuum cleaner's LiDAR to the cloud, where a remote attacker performs further analysis to recover the original audio. In this way, a remote attacker is able to recover privacy-sensitive information from a victim through LidarPhone. LidarPhone operates under the following threat model. The attacker's goal is to conduct a remote, stealthy eavesdropping attack. They like to steal digits, for example, social security numbers and pins, from the victim. The attacker's capabilities are assumed as such, that they can have remote access to the robot and the LiDAR data stream within it, and we know this is possible because we've done it. We also assume that the victim has a robot vacuum cleaner, speakers or a TV sound system, and objects nearby. So we know that robot vacuum cleaners have LiDArs with lasers, and the laser microphone can eavesdrop on audio from surfaces. So is LidarPhone just a spinning laser microphone? Not at all. LiDARs are designed for navigation with completely different requirements. Also, the attacker can only use the hardware on board the robot vacuum cleaner and cannot adjust anything, for example, receiving angles or the amplification level. There are also many other challenges which we will explain in the following slides. Firstly, we need a side channel on LiDARs to get any vibration information at all. While we expect LiDARs to just output a distance reading, they actually output two types of data. Assume that the LiDAR is not rotating and targeting a single point on a minutely vibrating surface, like this trash can. If we take just the traditional distance reading, we see only a constant signal since the distance from the LiDAR to the object doesn't change measurably. However, LiDARs also report the intensity, or basically the brightness, of the returned laser beam, which is used to filter out untrustworthy distance data usually. We find that this is a very useful side channel for LidarPhone and allows us to measure even these minute surface vibrations. But even with this laser intensity signal, LidarPhone still faces additional challenges during signal recovery. The first challenge faced by LidarPhone is the low signal-to-noise ratio of its recovered audio. To understand this, we first need to understand that there are two types of reflections. Firstly, specular reflections happen from highly reflective surfaces like windows and mirrors. These mostly maintain the intensity and the focus of the incoming light. Diffuse reflections happen from most other surfaces, which are rough on kind of a micro level. Here, incoming light is scattered in all directions. Laser microphones target specularly reflecting surfaces like mirrors and windows. As explained earlier, the vibrating surfaces cause a changing signal in the laser microphone. So what if a LiDAR targets a reflective surface? Now, robot vacuum LiDArs are only tuned for low light conditions since they are designed for navigations and the majority of objects are diffusely reflecting. So any specular reflections from windows and mirrors actually saturate the sensor, which appears as a flat line instead of the expected varying signal which we can pick up as an audio signal. Therefore, when LidarPhone targets everyday objects, it receives only diffuse reflections, which are low intensity and low SNR. The next challenge for LidarPhone is its low sampling rate. A LiDAR rotates about 5 times a second typically, or 5 Hz. That means a single point in a 360-degree arc of the LiDAR is only sampled at 5 Hz. We know from other work that we need 5,000 Hz for intelligible audio signals, and this 5 Hz for our audio signal from a rotating LiDAR is way less than this 5,000 Hz that we need. So, as a mitigation, we have to halt the LiDAR rotation during the attack. But even so, the maximum sampling rate we can achieve is only 1,800 Hz focused onto a single point. How we get this number is from the 5 Hz rotation rate multiplied by the 360 samples per rotation it normally takes, which results in 1,800 samples per second on an individual point. Now, we note again that this 1,800 Hz is still less than the 5,000 Hz threshold that we need for intelligible audio. So how do we solve these combined challenges of low SNR and low sampling rate? We solve it through specific modules in our system design. At a high level, we apply a machine learning pipeline of training during our bootstrapping phase and prediction during our attack phase. We take digit data, for example, as training data, we put it through our pre-processing pipeline, and take the corresponding ground truth labels as well, and combine them into a trained model. In the attack phase, we recover signals from a victim's robot vacuum cleaner, we pre-process those signals, and we ask our classifier to make a prediction as to what kind of data this might be. In this case, it's a predicted digit of 1. What's more important is that we know that our pre-processing module solves the first issue of low SNR, and our classifier solves the second issue of a low sampling rate. So to solve our first challenge of low SNR, we apply our signal pre-processing module. This image depicts a spectrogram with time on the x-axis, frequency on the y-axis, and the color indicating the intensity of that frequency. It shows a ground truth recording of the digit 0 through a traditional microphone, while it's downsampled to 1.8 kHz for a fair comparison. This is the upper bound or the best kind of signal we could possibly receive from LidarPhone. So let's take a look at what we actually recover. So this image shows a signal recovered by LidarPhone. Note the intense noise band in the middle, which overpowers any useful information around it. This is not yet a usable signal. To remove this noise, we apply 2 sets of pre-processing techniques. The first removes the yellow band of noise containing outlier data points, which is noise contributed by the LiDAR hardware itself. This restores something resembling an audio utterance. The second removes background noise, but also high-frequency noise, since our target objects tend to vibrate at lower frequencies when audio is played near them. We invite you to read our full paper to understand these effects and our pre-processing pipeline in more detail. But as a summary, we're able to achieve significant signal recovery. After pre-processing, we can compare 2 individual digit occurrences recovered by LidarPhone, 7 on the left and 8 on the right. Let's listen to them. We note two insights from these spectrograms and audio files. Because of our low sampling rate and noise, the digits are still not intelligible and we cannot distinguish between them. We can also note that the differences in digits is subtle, but we can find spectrogram image features that can differentiate them. To address the undersampling of the signal, we restrict ourselves to classifying from a set of words, for example, digits. In this case, digits 0 to 9 will allow us to classify social security numbers or pins. To address the subtle differences between digits, we use a convolutional neural network as an ideal tool for image recognition, and this leads to high accuracy, whereas traditional models do not perform well on this task, which we also evaluated. So we take our pre-processed time series signal, we convert it into a spectrogram, and we feed it into a convolutional neural network, which predicts a digit of 1 in this case. This is our audio classification system. So to understand if our system design really works, we evaluate LidarPhone through comprehensive real-world testing. We evaluate a work-from-home scenario with a computer emitting speech through speakers. We have a laptop with speakers and a subwoofer, a target object next to it, and a robot vacuum cleaner targeting that object. We actually evaluate another scenario of recovering the victim's political orientation based on the news programs they listen to. This is discussed in the full paper. We vary the objects that are targeted, the volume of the speaker, the distances between the speaker and the object, and many more as well. We play digit speech through the speakers from the TI digits and free spoken digit dataset corpuses. For gender and speaker classification tasks, the digit dataset contains 10 speakers, 5 male and 5 female. We now summarize the results of LidarPhone's comprehensive evaluation. We are accurate at classifying digit audio with up to 91% accuracy over 10 classes, basically the digits 0 to 9. We are robust against changes to background lighting conditions, background noise conditions, and even using lower quality lidars. We are also able to generalize across many different objects. For example, we can train on one kind of trash can and recover signals from a completely different kind of trash can. We also note that the system accuracy reduces as the volume of the speaker decreases and the distance between the speaker to the object increases, as expected. In the interest of time, we now present a selection of our results, but we invite you to read our full paper for all the details and plots. As overall results, we are able to recover significant information from speech. In this case, we play audio at a trash can at about a 70 dB volume, which is equivalent to a loud conversation. So the target object is visible on the left as a trash can, and on the right we see our results. The x-axis indicates the task we are evaluating, and the y-axis indicates the percentage for a particular metric that we are evaluating. For digit and gender classification, we're able to achieve over 90% accuracy, and for speaker classification, we're able to achieve about a 70% accuracy. Note that in a digit classification case, we have 10 classes, same for the speaker classification case, and we have 2 classes for the gender classification case, with a random guess of about 50% in that specific case. We propose a few ways to prevent a LidarPhone attack. Firstly, we should not allow lidars to fire their laser when they are not rotating. This limits the sampling rate to 5 Hz, which provides LidarPhone with very little useful information. We would also urge lidar manufacturers to only provide a process distance value to the user instead of also providing the laser intensity side channel that we discussed earlier. Moving on, to practically launch a LidarPhone attack, we propose a simple technique using already available capabilities of the robot. Now, a robot is able to search for target objects and areas using the maps that it already creates during cleaning. And after doing the cleaning, it can find all of these target objects and target them for a LidarPhone attack. In this map, we can see examples of objects that are in a traditional house, and we can see that some of these features are actually visible on the map. Take the desk in the bottom right-hand corner. We can actually see the 4 table legs that make up the base of this desk, and this is one way that robot vacuum cleaners and LidarPhone could identify which areas to attack. So in conclusion, LidarPhone uses lidars on robot vacuum cleaners to perform audio eavesdropping. We use a signal processing and machine learning pipeline to extract as much information as possible from our noisy environment. And we hope to alert the SenSys community that lidars are possible eavesdropping attack vectors, and to encourage research into defense strategies for such active sensor side channels. These include increasingly more common laser sensors in smartphones, for example the iPhone 12 and the iPad Pro, and even self-driving cars. Thank you, that's all I have. and I'm open for questions now.